Equilibrium and equilibrium constants are going to be the topics in this lesson. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, in addition to high school and college science prep, we also do MCAT, DAT, and OAT prep as well. You'll find those courses at chadsprep.com. I'll leave links in the description. Now, this lesson is part of my new general chemistry playlist. I'm releasing several lessons a week throughout the school year, so if you want to be notified every time I post a new one, subscribe to the channel, click the bell notification. All right, so we first got to start off with some definitions here, and the first is simply the definition of equilibrium. And in chemistry, we talk about what's known as a dynamic equilibrium. And the important part here is that when a reaction reaches equilibrium, the concentrations of reactants and products are no longer changing. And this is important. Back in first semester Gen Chem, we talked about like limiting reagent problems and things of this sort. And the assumption we made with those limiting reagent calculations was often that a reaction that went to completion until one of the reactants ran out. Well, it turns out that's not often that's not always going to be true, it turns out. Most reactions don't actually go to completion, and often or even close to completion. They're going to reach some intermediate, what we call equilibrium. And once they reach equilibrium, the concentrations of reactants and products are no longer changing. However, it's not because the reaction has stopped. It's just that the reaction is going in both the forward and reverse directions at exactly the same rate. And that way, every time we convert reactants into products, we're converting products back into reactants at exactly the same speed. That way the overall concentrations aren't changing. And that's what we mean by a dynamic equilibrium. A static equilibrium would decide just, something that's completely stopped. And that's not what we have typically in chemistry. We have this dynamic equilibrium, again, where the forward rate equals the reverse rate, and that's the definition of equilibrium you want to take home. Now, keep in mind, again, this means the concentrations aren't changing anymore. However, it does not mean that they are equal, and this is a huge misconception. At equilibrium, the concentrations of reactants and products do not have to be equal at all. For some reactions, they end up with a lot more products when they reach equilibrium. For other reactions, they end up with a lot more reactants when they reach equilibrium. And still yet, for other reactions, you're going to end up with a fair amount of both. But there's nothing that says they have to, in principle, be equal for any system that has reached equilibrium. For some small number, that might be true, but for the vast majority, it's just simply not the case. So again, it means that the forward rate of the reaction equals the reverse rate of the reaction, but it does not mean that the reactant concentrations and product concentrations are equal. Now, in addition, you should know that we're going to talk about what's called an equilibrium constant. So in this equilibrium constant, we're going to symbolize with the letter K, and it's going to be a capital K. And I point that out in this case because in the last chapter on kinetics, we used a lowercase k to represent the rate constant. And we saw that with a rate constant, they were affected by temperature, and they were affected by when you add a catalyst, because that lowers the activation energy. So it was affected by both temperature and activation energy. Well, this equilibrium constant, the only thing that can change it is a change in temperature. If you add a catalyst, it doesn't change. So if you change the activation energy, it doesn't change. But only a change in temperature is actually going to lead to a change in the numerical value of an equilibrium constant. So we'll find out a little bit more about what these means, but almost always when they give you an equilibrium constant, they're going to specify what temperature it applies to, because if you change that temperature, it's probably going to change the value. All right, so it turns out this equilibrium constant is equal to the ratio of the concentrations of products to the concentrations of reactants raised to the power of their coefficients. And you should know that typically only aqueous and gaseous species show up. No solids, no liquids. Now, technically, liquids might show up if they are not the solvent. So if you got some liquids in combination, but none of them is actually the solvent. Well, it's when the liquid is a solvent that it's not going to appear. So in the odd case, and this often happens more like in a particular laboratory experiment you might do, you might see some liquids, but in the lecture, you're probably not likely to see liquids showing up in these equilibrium constant expressions. And so in this case, we're going to say it's the ratio of the concentration of the products, CO, raised to the power of their coefficient. So it's got a coefficient of 2, so products on top in the numerator here. And these brackets mean molar concentration relative to the concentrations of the reactants. And notice we're leaving carbon out of this because carbon is a solid. And it turns out that solids have an activity of 1, we say. And so technically, if you put its activity down here, if you take an advanced thermodynamics course, you actually find out that instead of concentrations, it's really activities. And solids have an activity of 1, and anything multiplied or divided by 1 is itself, and it doesn't affect the equation. So that's ultimately why solids and liquids are going to stay out of here. They have an activity of 1 in most cases, and so they just stay out. Well, in our cases, we're not talking about activities. We're simplifying this in Gen Chem. We're just going straight to concentrations of either aqueous or gaseous species. Now, in this case, we've got, again, the concentration of CO squared all over the concentration of O2. However, for reaction involving gases like we've got here, you might also use partial pressures instead. And so you might also give this ratio a little bit different and say partial pressure of CO squared all over the partial pressure of O2. Now we've got a problem because partial pressures and molar concentrations are not necessarily equal for gases. So if you come take a look at the ideal gas law for a second, and so say PV equals nRT, you'd see that we can relate pressure to molarity here in kind of a unique way. So pressure is going to equal N over V times RT. If I solve for P here and divide through by the volume, moles over liters is molarity. And so we see that pressure and molarity are not equal. There's this extra factor of RT that's going to be important, as we'll see in a little bit. And so it turns out with gases then, you have two different ways of expressing the equilibrium constant. And because pressures and molarities are not equal, then the equilibrium constant values themselves won't necessarily be equal. And so we've got to actually define two types of equilibrium constants. If you express it for gases in terms of molar concentrations, we'll call it a Kc value. And if you do it in terms of partial pressures, we'll call it a Kp value. And these are kind of the proper designations. And we'll find out a little bit that Kp and Kc under certain cases might be equal in value, but most of the time they won't. But we'll see how to kind of, if you're given one, figure out the other here in a little bit. Now in general chemistry, it's quite common to generically just use the term KEQ. And based on context, you got to kind of figure out, are they talking about Kc with molar concentrations, which is probably most of the time. And if it's a reaction involving only aqueous species, it would have to be a Kc. They don't have Kps. But technically this is generic, and technically it's kind of improper. If you were taking an advanced thermo class or advanced physical chemistry class, you wouldn't see this showing up there. They're either going to use Kc or Kp. They're never going to use KEQ. So it's kind of an improper term, but we use it in general chemistry all the time, just so you know. But I'm going to refrain from using it. I'm going to try and do my best to be proper. I just wanted to give you a heads up in case you see it in your class or in your textbook. Okay, so these equilibrium constants, again, are constants. The only thing that can change them is a change in temperature. Now, one thing to note, we actually got to get a little tiny bit more specific than this. So it turns out these concentrations have to be measured at equilibrium. And I'm writing this in red because we never specify this. I'm adding this myself. So you know, this is the concentration of CO for a reaction that has reached equilibrium, and this is the concentration of O2 for the reaction that has reached equilibrium. But that's kind of implied when you set this ratio equal to K, as it turns out. So we don't actually write the EQ there, it's just implied. So what if the reaction hasn't reached equilibrium? Well, then this ratio, wouldn't actually equal your K value yet. And we'll find out in the next lesson, there's something called the reaction quotient that looks at this same exact ratio for a system that doesn't necessarily have to be at equilibrium. So I just want to allude to that for the future. Cool. So big thing about these equilibrium constants, they're super handy because by a single numerical value, you can figure out, is this a reaction that's going to end up with a lot of products or not so much? If you work in an industrial factory and stuff like this and you want to make a lot of a certain particular chemical, well, then the hope is that it's a reaction where you can make a lot of that chemical. So let's take a look at what I mean here. So it turns out you're going to have one of really three scenarios. You're either going to have an equilibrium constant that is a lot greater than 1, an equilibrium constant that is a lot smaller than 1, or you're going to have an equilibrium constant that's somewhere in between. And when we say in between, oftentimes we actually set the outer boundaries for what we mean by in between. And so for an equilibrium constant that's close to 1, so that's really kind of nebulous, and you're going to be like, that's not very close to 1, Chad. Well, it's just kind of the boundary, sorry. But if it's in between 0.001, 10 to the negative 3, and 1,000, 10 to the third, that's what we're going to say is K that is close to 1. And depending on where an equilibrium constant lies, if it's in this range, or this range, it's going to tell you something important about this reaction. Now, in the case where your equilibrium constant is a huge number, like let's say it's equal to 1 billion, 10 to the 9th, well, in that case, that means you're going to have a very large numerator and a very small denominator in comparison. Your numerator is going to be way bigger than your denominator. Well, that means you're going to have way more products than reactants when that reaction reaches equilibrium. And to describe that, we say that that reaction favors the products at equilibrium. And that'd be the ideal scenario if you're trying to make this particular chemical in your industrial factory. If it's the product of the reaction, then it'd be really convenient if it has a very large equilibrium constant, because when that reaction reaches equilibrium, you end up with a lot of that product. Now, on the other hand here, if your equilibrium constant is way smaller than 1, like let's say instead of 1 billion, it's 0.000001, a really tiny number. Well, what that's going to indicate is that you have a very large denominator now, a lot of reactants, and a very small numerator comparison, a small amount of products. And so because you have lots of reactants and not very many products at equilibrium, we say that that reaction favors the reactants. Now, just because a reaction favors the reactants at equilibrium doesn't mean you can't make a lot of the product in that reaction, but it probably is going to be a little more difficult, and it might be a little more expensive to manufacture and things of this sort. But we'll find out in the next lesson there are ways to still shift the equilibrium, as we'll say in the next lesson, and actually still make a fair amount of that product. Now, your last scenario here is, again, for an equilibrium constant that's somewhere close to 1. And again, close to 1 means bigger than 0.001, smaller than 1,000. And in this case, it doesn't really favor the reactants or the products, we say, but you're going to have a fair amount of both. Now, these are kind of somewhat arbitrary where we set these boundaries, but they're kind of given good liberty to what approximately 1 or close to 1 means. And the reason they do that is because the number of products and reactants you might have don't have to be that similar in some cases. So if you notice here, we've got in the numerator, we've got a squared term. In the denominator, we don't. And so notice, let's say that both these concentrations were equal. Let's say that, I had 10 molar O2 and 10 molar CO for some, reaction that reached equilibrium at some temperature or something like that. Well, if these are both equal to 10 molar, they're equal. However, notice your equilibrium constant is going to be 10 squared over 10. So 10 squared is 100 divided by 10 equals 10. And so even though you have equal amounts or equal concentrations of reactants and products, that doesn't actually indicate an equilibrium constant that's exactly equal to 1. And that's the difference of having a square on top and only having it to the first power on bottom. And you have other cases where it's not just the difference between a square, and a first power, but maybe a cube or to the fourth power or something like that. And so you can end up with big differences or big deviations of your equilibrium constant away from 1, but still have roughly equal amounts of reactants and products. And so that's why they give huge liberty to saying approximately 1 or close to 1. Well, again, bigger than 0.001, smaller than 1,000. Cool. So now if I give you an equilibrium constant, if I say, actually, if we look at this reaction here, so at kind of normal room temperature here, this is a combustion reaction. It is very spontaneous, we'll learn later in the semester. And it goes almost entirely to completion like most combustion reactions do. Now, this is only partial combustion, but it's still highly, highly favorable. And it goes virtually to completion. If you actually looked up its equilibrium constant at a certain temperature, like say 298 Kelvin, you probably find it's like 10 to the 40th or 10 to the 50th. It is a ginormous number. And when you see a number that is that big, you know that it heavily favors the products. In fact, if it's that big, like 10 to the 40th, 10 to the 50th, it virtually goes to completion. So just an FYI. Now, on the other hand, if you have an equilibrium constant that's at the other end of the spectrum, like let's say it's 10 to the negative 10. Well, if you have an equilibrium constant on par of 10 to the negative 10, well, then it's going to heavily favor the reactants. You're going to have way more denominator than numerator for that reaction to equilibrium. And then finally, if I said like your equilibrium constant is equal to like 13, well, 13 is definitely in this range, and you're probably going to have a fair amount of both reactants and products. And you might be like, well, maybe more products, but not necessarily. Really depending on the, how many squares and stuff you have in numerator and denominator, but it is in this range if I said it had a value of 13, and so it would have both reactants and products at equilibrium. So that's what an equilibrium constant ultimately allows us to do. From a single number, we know something about how much product we can make from that reaction. Now let's take a look at Kp and Kc one more time. So we said that, again, these don't necessarily have to have the same value. So, and again, we only have Kcs and Kps for reactions that involve gases. If you only got aqueous species, you're only going to talk about Kcs. There's no Kps for those. So it's only for reactions that involve gases that you can have these Kps as well. And again, Kc and Kp don't have to be numerically equal, but they might be. So let's go back and take a look one more time. So we rearranged the ideal gas a little bit ago and said that pressure equals molarity times RT. And so if you were to take and substitute for every one of these pressures here, the molarity, the molar concentration times RT, well, you'd end up with a molarity on the bottom, just like here, and a molarity squared on top, just like here, but you end up with an extra factor of RT on the bottom and an extra factor of RT all squared on top, and they're not going to cancel. So you've got that extra factor of RT you've got to factor in. And there's an equation for this. So in the equation just goes Kp equals Kc times RT to the delta N power. And delta N here refers to the change in the number of moles of gas only gas. And so notice if that change in the number of moles of gas is 0, well, anything to the 0 power is 1, and anything times 1 is itself. And so if delta N is 0, i.e. you have the same number of moles of gas on the reactant side as on the product side, for that case and that case only would Kp equal Kc. But if delta N doesn't equal 0, then Kp and Kc won't be equal. And so you might get a question on the test that just says, for which of the following reactions would Kp equal Kc? And you don't have to do any calculation here. You just got to look and say, okay, for which of the provided reactions is there an equal number of moles of gas on the reactant side and on the product side? And again, leave out the solids, leave out the liquids, leave out the aqueous. It's delta N here is only the change in the number of moles of gas. So like in our reaction here that we've been looking at, leave out the solids, but we have 1 mole of gas on the reactant side, 2 moles of gas on the product side. Kp is not going to equal Kc. And in fact, that's the next thing we're going to look at is a calculation involving this reaction. Because that's the other thing you might have to do. You might actually have to do the math here, and you might be given Kc and asked to calculate Kp, or given Kp and asked to calculate Kc. Either one of those could show up, and that's what we're going to take a look at here. And so question on the study guide here says, if for this reaction, which has Kc equal 1200, and it says at 400 Kelvin. And so in this case, it turns out again that the one thing that can change the value of an equilibrium constant is temperature. And so oftentimes when you're given an equilibrium constant, you're almost always going to be given the temperature at which that equilibrium constant applies. Because if the equilibrium constant Kc here is 1200 at 400 Kelvin, well, at 300 Kelvin, it's going to be a different number. At 200 Kelvin, it's going to be a different number yet, and stuff like that. And so almost always when they give you an equilibrium constant, they're going to specify what temperature it applies to. And just keep in mind that the temperature is not necessarily going to be used in every calculation you see. It's just proper to give you a temperature for which that equilibrium constant applies. But in this case, we're definitely going to use that temperature as part of this. So we're given Kc, we're being asked to find Kp. Let's do some plugging and chugging here. And so we've got Kp equals 1200. Now, we haven't talked about units yet, but these equilibrium constants are unitless, it turns out. And you might be like, wait a minute, Chad, that's not possible, because you got the molarity here squared over molarity here. Molarity squared divided by molarity is actually molarity, Chad, not no units. I know, and that's the problem here. Technically, I told you that we write in the little EQs here, but they're not really there, It's implied if you set it equal to K that you're measuring these concentrations at equilibrium. Well, the other thing that we often don't write in, and we'd be a little more explicit about in a PChem class or something like that, is that technically we're always going to divide every concentration by unit molarity, 1 molar. And so here would be the concentration of CO over 1 molar all squared. And you have molarity over molarity, and the units cancel. Here you have molarity over molarity, and the units cancel. And we don't write this in, but it turns out it's also implied. It actually is technically a part of what an equilibrium constant is, but you're not likely to see it in a Gen Chem class. But for that reason, equilibrium constants never have units. Notice it's not the same as rate constants. Rate constants always had units, and it all depended on what order the overall reaction was and stuff. But equilibrium constants are always going to be unitless, at least that's proper. All right, so we got an equilibrium constant of 1200. And in this case, we've got this RT. And in this case, your R is going to be the 0.08206 liter atmospheres per mole Kelvin. This is the one you're going to end up using. Now, if you look here, this was the value used when we did PV equals nRT ideal gas calculations, although for much of this second semester, you're going to be using the one involving energy, more proper, SI energy units, the joule, the 8.314 joules per mole Kelvin. When you're dealing with energy, you're almost always going to be using that value. But anything that goes back to PV equals nRT, in fact, that's derived from PV equals nRT, is still going to be using this value. In all likelihood, because you're going to be using both this semester, you're probably going to be provided with both, and you got to know when you're going to use one versus the other. Well, again, anything involving gases back in chapter 10 that we saw, or in this one place, in this formula right here, this is the one we're going to be using with the liter atmospheres per mole Kelvin. But any other context it's likely to come up in general chemistry, it's probably going to be coming up in terms of energy, like we saw it with activation energy in equation last chapter, and that was customary to use the 8.314 joules per mole Kelvin. So I just want to make sure you realize which value you are going to use. Now in this case, it's the only one I'm providing you with, but on an exam or homework, you got to know that, oh, this is the one place in second semester, you're likely to have to go back and use the value we used back with PV equals nRT stuff. All right, so here we've got this 0.08206 liter atmospheres per mole Kelvin. And then temperature, in this case, again, 400 Kelvin given in the question. And then we got this delta N. So we're going to put this in brackets. And then the delta N, again, is the change in moles of gas. And a change in anything is always final minus initial. And so the final number of moles of gas we end up with is 2, and the initial number of moles of gas is just 1. And again, we're ignoring the solids. And so final minus initial, 2 minus 1, is going to be positive 1. And so this is going to be raised to the positive 1 power. And that just signifies that we're increasing by 1 mole of gas. And going from 1 mole of gas to 2 moles of gas, that's an increase of 1 mole of gas total. So, and that's what actually that delta N signifies. So when it's an increase and you have more on the product side, it's going to be positive. And when you have a decrease, there's more on the reactant side, then it's going to end up being a negative delta N in that case. All right. So, and from here, it's just plugging and chugging. So let's pull out our calculators. And so in this case, we're going to take 1200 times 0.08206 times 400. And we don't have to square it or anything. It's just to the 1 power. And so we're going to end up with a Kp value. In this case, 39,388.8, and I'll probably just round that to a couple of sig figs and round it to 39,000. And again, also unitless. So the Kc value is 1,200, the Kp value is 39,000. Notice they're not that similar in this case. But that's pretty typical. But notice both of these you would have probably recognized as meaning the reaction is going to favor the products. They're both bigger than 1,000, so quite a bit bigger than 1. All right, the last thing we're going to do in this lesson is we're going to look at one reaction we've been given the value of the equilibrium constant for. It's equal to 16 in this case. And then we're going to be given some related reactions and asked to give a numerical value for their Kc values, their equilibrium constants as well. And so if you look, these reactions can't just be random. They've got to be related to the first one we've been given the Kc value for. And so if you look at this top reaction, you look at the one right below it, how are these related? Well, if you look, the second reaction is just the exact reverse of the first reaction. And that's going to be, there's going to be a relationship we can derive from that. Now, a lot of students see, oh, it's reversed. I guess if, Kc here is equal to 16, maybe here it's equal to negative 16. Well, equilibrium constants are never negative, so we could just scratch that right off the bat. If they're just concentrations of products of reactants, the only way they can come out negative is if you have a negative concentration, which is impossible. So no such thing as negative equilibrium constants. So we'll come back to that in a minute. If you look at the next one here, how does that relate to the first one? Well, it's the same thing as the first reaction with everything cut in half. So, and it turns out, again, you might be like, well, if I carried this reaction out in a beaker, whether I wrote it like this or wrote it like this, it'd be the same reaction. So I've got SO2 mixing with O2 to form SO3, just like we do here. However, if we change the stoichiometry, we treat this as a different reaction. And so you might realize, earlier I said that the only thing that will change the value of an equilibrium constant is temperature. And what I mean by that, though, is in such a case like this, if you change the stoichiometry, you have changed the reaction. I realize if it's happening and occurring in a beaker, it's the same reaction. But if you change the stoichiometry, we view it as a different reaction, and it will change the value of the equilibrium constant, as we'll see. But in this case, you find out that we've cut all the coefficients in half. And before you think, well, that might cut the equilibrium constant in half, maybe it's equal to 8. Well, you'll find out that's wrong again as well. But based on our definition of equilibrium constant, we'll see why that is, and we'll get a nice little pattern for it. And then finally, for this last one, it relates to the first one in the fact that it's reversed. You're going to go in the reverse direction and cut everything in half. And we'll see how that plays out. Now, to help us do this, I'm going to put the equilibrium constant expressions for every one of these reactions up on the board to make this a little easier to see. All right, so we're going to start with this first one here, or the second one, I guess, really technically. And if you look at the expressions here, for the first one, products over reactants is SO3 squared over SO2 squared times O2. Whereas for this one, which is again the exact reverse reaction to the first one, we've got written out here. So again, products over reactants now looks like so. And if you look at the expressions, so you'll see that this is the exact inverse of what we had up here. And so if this one is equal to 16, and notice that 16 is the same thing as saying 16 over 1. Well, if you flip this over, then you're going to get an equilibrium constant now of 1 over 16. And you can put that in your calculator to find out what that is in decimal form or something like that. But it's 1/16. And so what we've just learned now is that reversing the reaction just based on how equilibrium constant expressions here are defined, products over reactants raised to the power of the coefficients, reversing the reaction inverts the value of the equilibrium constant. So for the first reaction, Kc was equal to 16. For this second one, that's the reverse reaction, it's now 1 over 16. Okay, so let's take a look at the next one here. Let's get a Kc expression up for this one as well. Okay, so for this next one here, relating it back to the first one here again, it's in the same direction, but all the coefficients are cut in half. 2's become 1, 1's become 1/2, 2's become 1. And with all the coefficients cut in half, well, don't forget that in the equilibrium constant expression, your coefficients show up as the powers. And so if you're cutting all the coefficients in half, you're cutting all the exponents in half in your equilibrium constant expression. And cutting your exponents in half is not the same thing as cutting the number in half. And so our Kc for the first reaction, 16, the Kc here is not going to equal 8. You don't just divide it by 2. You have to take the 1/2 power when you're cutting exponents in half. And the 1/2 power means square root. And so in this case, your Kc is actually not going to equal 16 over 2. It's going to equal the square root of 16, which is 4. And so cutting your coefficients in half, square root. Cutting them by, to 1/3 of their value, cubed root. Doubling them, square the equilibrium constant value. Tripling them, cube the equilibrium constant value. That's kind of how that works. And again, you can figure it out if you just do a simple comparison of the equilibrium constant expressions, but that's kind of time consuming. And on the exam, you want to get to the point where you can look at the relationships. Is it forward? Is it reversed? Is it doubled? Is it halved? Those kind of things, and be able to figure out what the equilibrium constant is going to be without even having to write these expressions out. But in a pinch, if you still need to write these expressions out to figure out how they're related mathematically, great, it'll still lead you to the right answer. So let's take a look at this last one here. In this last one, we not only reverse the reaction, we also cut it in half. All right, so there's our expression, and if again we related this back to the first one, we'd see that not only is it reversed, but also all the equilibrium constant, all the coefficients are cut in half, which again means square root. So reversing it means take the inverse. Cutting all the coefficients in half means take the square root. Now we've got to do both. We've got to inverse it and take the square root. And it doesn't matter which one you do first. They're linear operations, so order doesn't matter, it turns out. And so in this case, if we start with 16, I can invert it and get 1/16, and then take the square root and get 1/4. So, and notice if you did it the other order, it'd be the same thing. If instead you want to take the square root first, square root of 16 is 4, and then inverting it would get you 1/4. Cool, but these are the kind of relationships, again, you might be on the hook for. Make a great exam question. I just wanted to show you some patterns here. You want to get good at this before the exam again to save yourself some time. But if at the end of the day you need to write these out, it will still lead you to the right direction, just a little more time consuming. Now, if you found this lesson helpful, that thumbs up button goes a long way to letting YouTube know that other students should see this lesson as well. And if you're looking for practice problems on equilibrium, check out my General Chemistry Master Course. I'll be sure to leave a link in the description. Free trial is available. Happy studying.